Hello everyone. Very good afternoon to all. Welcome to today's webinar on formation and oxidative aging of secondary organic aerosols using potential aerosol mass oxidation flow reactor. In short, it is called PAM. I am Satyanarayana from Tescon Aerofluid Incorporated in Bangalore. Our company for over 25 years has been providing research instruments and technical support for instrumentation which are used for atmospheric sciences, aerosol size and chemistry, black carbon, and measurement of specific meteorological variables. We are located in India, Singapore, Turkey, and USA. Currently, our instruments have been used in various campaigns to measure aerosol mass and size distribution, airborne particle studies, atmospheric trace gases, clouds, and radiation. Also, we continue to expand our atmospheric instrumentation and real-time monitoring capabilities. I would like to introduce to you today's presenter, Dr. Andrew Lambe. He is a senior research scientist at Center for Aerosol and Cloud Chemistry, Aerodyne Research Incorporated, USA. Dr. Andrew will provide an overview of how PAM generates secondary organic aerosol from the oxidation of precursors and also how it can be used to characterize particle, chemical, physical, and optical properties over simulated photochemical aging timescales. During the session, if you have any questions, then please put it into the chat box. At the end of this session, we will have a question and answer session. We will try to cover all your questions in that. If you are facing poor video or audio quality, please click on the Reconnect tab, which is at the top of the window. You can watch our previously conducted webinar recordings in the blog section of our official website. Thank you again for joining us. I request Dr. Andrew to start the session. Over to Dr. Andrew.
Thank you, Satya, for the introduction, and thank you all for joining us today. It's my pleasure to talk to you about my company, Aerodyne, and our research. And let me just start by saying that my email address is here. If you're interested, you can send me an email afterwards and I'll send you the slides. There's no need to take screenshots or notes while I'm talking unless you'd like to. And with that, I'll begin. So an outline for my talk, I'll start with a background as an introduction to Aerodyne, for those of you who may not be familiar. And then I'll introduce the concept of oxidation flow reactors, or OFRs, before I get into some of the specific discussions of the PAM OFR. And then I will show some select laboratory and field applications of OFRs to give you a sense of how they can be used to gain insight into sources and aging of SOA in the atmosphere and in the lab. So just to start, a brief introduction to Aerodyne. We are a small company that was founded in 1970 and is located in the suburbs of Boston, Massachusetts, in the United States. We have about 70 scientists and support staff in our company. When we were originally founded, we were mostly a defense contractor, but we have since evolved over the last 50 years to a company that now does research and development of instruments as well as consulting services. And we have 5 research centers today. I am in the Center for Aerosol and Cloud Chemistry, which is the largest group at Aerodyne, but there are many other active and thriving research centers in our company also, including some that make instruments, such as the Center for Atmospheric and Environmental Chemistry and the Center for Sensor Systems and Technology that have delivered instruments to India. Our previous president was Chuck Kolb, who sadly passed away early last year, and our current president is Dave Nelson. To date, we've delivered, with Tescorn's help, more than 17 research instruments to India, to the 6 groups that I've shown at the bottom. And we hope that this is the start of a continuing collaboration with research groups in India that will continue to grow over time. We have delivered instruments to IIT Kanpur, IISc, PRL, VSSC, IIT Pune, and IIT Delhi. The instrument that Aerodyne is best known for is our aerosol mass spectrometer. This is an instrument that can provide a real-time chemical fingerprint of suspended aerosols in the air through a high-resolution time-of-flight aerosol mass spectrometer. It can also provide sizing information of organics and inorganic ions such as ammonium, chlorides, sulfate, and nitrate. And it can do this in timescales of 1 to 5 minutes under typical atmospheric loadings. Another very similar instrument, but more of a monitoring type instrument instead of a research instrument, is our aerosol chemical speciation monitor. And this has been the instrument that we've delivered most to India to this point, to the groups shown below. And so it serves a similar purpose, that it measures the chemical fingerprint of suspended aerosols in the air under 1 micron in diameter or under 2.5 microns in diameter, depending on the configuration of the instrument. The major differences being that it has unit mass resolution, unlike the AMS, which can resolve to much better than 1 unit mass, and it does not provide sizing information. But it's used routinely, and it is the instrument that we delivered most to India to date. We've also delivered a VOCs proton transfer reaction mass spectrometer, which can be used to measure VOCs and OVOCs with high sensitivity and high time resolution in the air, and it can be coupled to a gas chromatograph to get isomer-specific information about VOCs and OVOCs. We have delivered 3 cavity attenuated phase shift analyzers that are configured in different ways to either measure the aerosol extinction and scattering, or it can be configured as a gas phase analyzer to measure NO2 mixing ratios in the air. And then finally, what will be the focus of the talk today, we've delivered 1 PAM oxidation flow reactor to the group in Delhi. And as with that instrument and with all these, as I said, we hope that this is going to continue to grow into the future through research collaborations with groups in India and government and universities and so on. This figure shows AMS measurements of aerosol composition in measurement sites around India, in Delhi, Kanpur, Chennai, and I'm going to not pronounce the last ones correctly, so I won't try. But I would imagine that a lot of you are familiar with this paper by Gunther et al. That summarizes this information in the context of discussing high aerosol chloride concentrations in the aerosol, which is shown by the purple pie charts in these graphs. And that's the focus of that talk. But this figure, I think, also nicely lays out some of the general trends that are observed in aerosol composition that motivate some of the research goals that I'll talk about today. The main one being that all of these subcomponents of non-refractory submicron aerosol, chloride, sulfate, nitrate, ammonium, and organics are all present and are all important in different source regions. You see that this green one, the organics, is always the dominant component of these aerosols. It's always at least 50%, and in some cases approaches 80%. And we tend to see that elsewhere in the world also, that organics are always, are often, if not always, the major component of submicron aerosols that is measured by the AMS. Organic, within that though, the context though, the organics are really complex. They're hundreds, thousands, tens of thousands of individual molecules, and they come from primary sources as well as are secondary of nature, being formed in the atmosphere from gas to particle conversion processes. And this figure illustrates that the dynamic nature of the primary to secondary split in India, where depending on the time of year, the time of day, and the source region, you can have primary organics that are the dominant component of that organic component to aerosols, approaching 80%, shown on the top right in subpanel F, or approaching 0% during the middle of the day when photochemical activity is highest, and there's significant contributions from secondary organic aerosols that are being formed from the oxidation of gas phase precursors. So this lends the question, what are the precursors to OA, which we often use interchangeably with SOA because it's the major component of OA, and how do we gain insight into the contribution of those different precursors to the organic aerosols that are being measured in the air. Traditionally, this has been these types of field observations have been supplemented by complementary studies in the lab, where research groups have used environmental chambers to introduce simple SOA precursors or mixtures of fixed VOCs that are thought to be important SOA precursors, and study their formation and aging over timescales of multiple hours to, in some cases, approaching days of real-time oxidative aging in the chambers. The state-of-the-art environmental chambers can mimic 1 or 2 days of equivalent aging time in the atmosphere in the lab with these large batch reactors that are used to study these processes. These are the most established method for laboratory SOA generation. They've been used for a long time, and they're widely accepted around the world as the most common means to do this. So they have a lot of advantages, and a lot of great research has been done with them, but they have some disadvantages that sometimes limit their applications in practical situations, including some that I've summarized in this bottom bullet point here, that in general, chambers, because they're so large, they're extremely resource intensive to maintain. They're relatively slow. It takes a day or multiple days to do a single experiment. And as with any large reactor volume, they are sometimes prone to contamination issues and over time, wall losses of particles and gases that can complicate the interpretation of some experiments. More recently than chambers, oxidation flow reactors, or OFRs, have been starting to be developed and introduced into the atmospheric chemistry community as a means to complement and extend the capabilities of environmental chambers, both for laboratory SOA generation and also in situ oxidative aging leading to SOA formation in field measurements, where it's not always practical to deploy smog chambers. Unlike most smog chambers, OFRs are operated in a continuous flow mode where a carrier gas of air and then trace levels of precursors to OVOCs and SOA are always introduced at the inlet, along with precursors to making specific oxidants like hydroxyl radical or nitrate radical or other oxidants are continuously introduced, and the steady state distribution of oxidation products is measured at the outflow with whatever measurement techniques are being used. And so one of the fundamental differences between chambers and OFRs is that in chambers, you're doing experiments that take hours to days to simulate days of equivalent aging time in the atmosphere, whereas in OFRs, these are done in timescales of minutes. So it's a semi-real-time measurement of the OVOC or SOA formation potential of precursors that are present in ambient air if it's being used in the field, or of the precursors that are being introduced in the lab if it's a lab study. The PAM OFR is the OFR that I'll be talking more specifically about in this presentation, but you should be aware that this is one of many OFRs that now exist in the community. These are often custom home-built instruments. They span almost as wide a range of volume as do chambers, with the smallest that I've chosen to show here, the microsmog chamber, a volume of less than 0.1 liters, to the largest, the photochemical emissions and aging reactor made by a group in Finland that is about 140 liters. So 4 orders of magnitude in volume for OFRs, but the characteristic that they all generally share is that they're trying to mimic days of equivalent aging time in minutes or less than a minute within the residence time of the OFR here. How are oxidants generated in OFRs? They all vary slightly differently in terms of the details of how this is accomplished, but the main network of reactions that use to generate hydroxyl radical, which is what OFRs are most commonly used for, is shown here. So hydroxyl radicals, which are the main oxidizing agents in most source regions during the daytime, are generated from starting with oxygen, which is photolyzed at 185 nanometer radiation, either external to the OFR to make ozone in a separate ozone chamber, or in situ to generate ozone and then photolyze it at 254 nanometers to make OH radicals from reaction of O singlet D atoms with water vapor, which is the main source of OH in the stratosphere and in many lower parts of the troposphere also. Along with that, if the 185 nanometer radiation is used inside the OFR itself, you get additional OH and HO2 production from direct photolysis of water vapor itself. And then if the experiment is trying to look at specific NOx-dependent chemistry, one can add nitrous oxide to photolyze at 185 nanometers to make O-singlet D atoms, which then react with N2O to make NO. And N2O can also react with O-singlet D that's formed from ozone photolysis to make NO as well, which with the ozone that's already present results in a steady state distribution of NO and NO2 for NOx-dependent studies in the OFR. Other oxidants that can be used and that are being used include ozone, which is already present for OH generation, but can be used in dark ozonolysis conditions. Nitrate radicals to look at the nighttime photochemical aging of VOCs and OVOCs, as well as chlorine and bromine to look at the influence of halogen atoms. So these techniques are all in various stages of development, and I won't be talking about them in detail today, but just be aware that those are additional systems that can be used to study SOA and formation and aging in OFRs. So how does this work in practice? Well, as I mentioned, the OFRs are operated in steady state, continuous flow mode, unlike most environmental chambers, which are operated in batch mode. And so what happens in practice is, this is an example time series of OFR data from the PAM OFR, where over time, we're stepping through different steady state conditions. Here on the top is the irradiance, which is proportional to UV intensity. So we're changing the intensity of the UV photons in the OFR to change the rate at which hydroxyl radical is generated and the amount of aging time that's formed. So here we're stepping down, and there we're stepping up, just to illustrate how that works. But each of these steady state periods can be maintained indefinitely if the user wants. Here I'm just doing it every few minutes to illustrate a typical measurement resolution that might be done in the field. In this case, we have 185 and 254 nanometer photons inside the OFR. So ozone is correlated with the UV intensity. When there's more UV, we're photolyzing oxygen more efficiently, we're making more ozone. But then when we step down the lab intensity, the ozone concentration goes down, and then it goes back up with the UV intensity. And so you can see that, with under typical conditions, we're generating tens of ppm of ozone to generate days or weeks of equivalent aging timescales by hydroxyl radical. And here, this time series shows SO2, which we've introduced as a reactive tracer, which can be used which is one way to infer the OH concentrations that are being made. If you have, this is called the tracer decay method. If you have a species with a known reaction rate coefficient with OH, you can measure its decay, and from the kinetic rate equations that govern its formation and its oxidation, you can calculate the integrated OH exposure or the photochemical age using this type of method. And you can see that when the UV concentration and the ozone concentration are the highest, the SO2 concentration is lowest, because this is where the OH concentration is maximized. But then when we back off the UV intensity and we're making less OH, the SO2 concentration approaches what it was before we turn the lights on. Another tool that has been developed to more comprehensively characterize OFR conditions in the PAM OFR, as well as other OFRs that use the same photochemistry, is this open source photochemical box model that was developed by Bill Brune at Penn State, who introduced the PAM concept that I'll be talking about in a couple slides, and that has been refined by other groups over the last few years. And I don't intend to go through every reaction that's shown here, but just to illustrate that there's a lot of reactions that govern, that describe the formation and the decay of individual radicals, including OH, but not limited to OH, and where this complements the type of tracer decay methods that I showed on the previous slide to infer OH concentrations, are that here you can model the concentrations of radicals that are really not possible to measure in any straightforward manner, such as O-singlet D or other really short-lived radical species. So this complements explicit measurements of OH concentrations by giving you a more comprehensive picture of what's happening in the OFR under different conditions. And so that's nice, but that type of model representation is not really possible to do in real time while measurements are being made. And so it serves a useful analysis purpose, but is not quite as useful as an online real-time diagnostic purpose. We and others in the community have also developed what are called estimation equations that are simplified algebraic representations of the model over a range of conditions that are summarized in this equation that we developed in a technical note recently. And so this equation allows the user to parameterize the OH exposure as a function of the external OH reactivity of VOCs that are being added, the ozone mixing ratio, the humidity, and the resonance time. And what put into practice, within a factor of 2 or so, over several orders of magnitude, this equation estimated OH exposure agrees with the OH exposure that is calculated by the model using the network of reactions I showed on the previous slide within about a factor of 2 or so. And so to give you a sense of scale for these large numbers that you're looking at here, 1 day of OH exposure in the atmosphere is about 10 to the 11 molecules per cubic centimeter per molecules per cubic centimeter second, which is in the mid-range of this plot. So this is looking at aging timescales that range from much less than a day to much more than a day. Yeah, this complements the model, and it complements the situations where you can measure the exposure by giving you a sense of where in a photochemical regime you are operating with the OFR at any given time. So now that I've introduced some of the general terminology and concepts around OFRs, I want to talk a little bit more specifically about the PAM OFR. This specific technique was introduced by Bill Brune, professor at Penn State, who introduced the concept almost 15 years ago now in a paper in ACP, where they defined PAM for a precursor as the maximum aerosol mass that the oxidation of that precursor can produce. And they demonstrated proof of concept of PAM using SO2 as a precursor to sulfuric acid, and showed quantitative conversion of SO2 to sulfuric acid over a range of SO2 concentrations in the early generation PAM reactor. And so this was the framework that Brune's group introduced, where they used an OFR to achieve the potential aerosol mass for SO2 and then other organic precursors that motivated follow-up studies in the community. But it turns out that while the concept of PAM is straightforward for inorganics like SO2 that only have a single oxidation product, the interpretation of that is more nuanced for organics, which make many oxidation products and whose composition is dynamic over a range of photochemical aging conditions. And I showed one example of that here, where I'm showing the yield of SOA formed from alpha-pinene, which is one of the most commonly studied biogenic VOC precursors to SOA. Here you can see that the yield increases at low OH exposure, increases as we produce multifunctional low volatility products, and then decreases again as these very low volatility multifunctional oxidation products that contribute to alpha-pinene and SOA are fragmented to make more aged but more volatile SOA. So the PAM concept, by the strict definition of the PAM term that I introduced on the previous slide, the PAM for alpha-pinene would be here, but depending on where the OFR is being operated, it's not a static quantity anymore, and we have to be careful how we apply that term. But that being said, the operating principles of the PAM and other OFRs hold as a tool to still study photochemical aging tables that extend and complement what chambers can do, especially in the field. And so to illustrate that, this slide shows the elemental composition of two types of biogenic SOA that are generated in one of the state-of-the-art smog chambers, the Caltech chamber, and the Paul Scher Institute chamber these squares here. This graph shows the hydrogen to carbon ratio and the oxygen to carbon ratio of the SOAs as measured by our AMS. And you can see that for the case of isoprene, the OFR is being used to significantly extend the range of oxidation conditions in both directions, not just in the more oxidized direction. For isoprene SOA, where we evolve towards much higher O to C and lower H to C as it's chewed up over multiple generations of oxidative aging. And then also with alpha-pinene SOA, where generally following the same trend as alpha-pinene SOA in the chambers as it evolves, and then extending it out further towards higher aging conditions that are comparable to multiple days of equivalent atmospheric aging. Aside from its specific geometry and hardware control systems, probably the most distinguishing factor of the PAM OFR compared to other OFRs is that we have been developing it and manufacturing it and delivering it to users all over the world for the last 5 years or so in collaboration with Bill Brune, who came to us with interest in co-developing this technique. So all of the other designs that I summarized in an earlier slide are mostly custom home-built configurations. Here, we have established a community that uses basically the same technique as we have with the AMS and ACSM and all of our other research instruments around the world, so that everyone is using basically the same hardware and doesn't have to develop that and can just instead focus on it using the OFR for its specific applications. And so Bill delivered several of the early generation PAM OFRs. Those are the blue markers on this slide, and those are primarily in the US and in Europe. After we took over the manufacturing and delivering components of the PAM OFR, we continued to deliver to the US and also to Europe, but more recently, most of the deliveries have been in China and elsewhere in Asia. And very recently, with Tescoran, we have delivered a system to Dr. Kumar's group in IIT Delhi. And so they have had the perspective of developing it over the last few months as a new group. But as it turns out, the first system that we delivered was to Dr. Chakrabarty at WashU St. Louis in the US, who I mention here because as is probably evident from his name, he's from India, and I know that he maintains active research collaborations with many groups in India. So I'm hopeful that, and I think there's a lot of untapped potential to use the OFRs for atmospheric sciences research in India and elsewhere. So what are some of the ways that OFRs can be used to gain more insight into SOA chemistry in India? I adapted this slide from my colleague by Joost de Gouw at CU Boulder, who was speaking in China a few years ago and was trying to motivate research studies that were centered around looking at the sources and the formation of SOA and the corresponding oxidation products through research collaborations in China. And I think a lot of the same questions hold true in India as well. An obvious question that I motivated earlier in this talk by asking what are the precursors to SOA is what fraction of SOA that's observed in situ from oxidation of precursors in ambient air can be explained by the consumption of VOCs that are explicitly measured. And so that can be done by coupling the OFR to a PTRMS such as our VOCs or any other instrument that is able to measure in real time gas phase compounds that might be reactive towards hydroxyl radicals and that might form SOA. It's also a logical question to ask what the gas and particle phase products are that are observed from the OFR as it perturbs ambient air, as measured with an instrument like the VOCs or another gas phase analyzer, and like the AMS or an ACSM or another instrument that's capable of real-time condensed phase measurements. And perhaps to the point of this talk, are they also observed in aged air masses, such that the OFR is able to provide insight into how the composition of ambient air changes as it's aged in the atmosphere. through direct perturbations of the air at the measurement location itself. So I'm going to show a couple of applications using the OFR to try to get at some of these questions in certain source regions around the world. Here is a time series of aerosol mass concentrations measured with an ACSM in a traffic tunnel in the US. And these measurements were made by Tachik et al. And during an afternoon rush hour period in the tunnel. Here, the OFR was situated in the top bore of the tunnel right above the traffic. So we're sampling emissions in real time from the cars going through, and we're aging them in the OFR and getting a semi-real-time indication of the SOA formation potential of the vehicles that are the mixed vehicle fleet that's going through. And so during this afternoon rush hour period, we sampled periods ranging from just a dark OFR with no aging to stepping up the lamp concentrations and going from hours to multiple days of equivalent aging within a few minutes residence time at the OFR. And you can see that without aging, when we're close to sources, we have typical primary organic concentrations in the range of maybe 5 to 10 microgram per cubic meter or so, significantly less in the way of inorganics. But then as we age the motor vehicle emissions, you start to see during these white periods, which represent when we're sampling through the OFR, significant concentrations of nitrate and ammonia, aerosol, as well as organics. So not only are we forming significant amounts of SOA, up to 40 microgram per cubic meter or so at multiple days of equivalent OH exposure in the OFR, we're also forming significant inorganic ammonium nitrate as well. In this case, our interpretation of that trend is the fact that when we're in a tunnel, there are high NOx concentrations and there are high ammonia concentrations as well. And so the NOx gets oxidized to nitric acid, and the nitric acid then gets neutralized by the ammonia to make ammonium nitrate. So this has been my experience using OFRs in different source regions. You oftentimes will see something that you expect, and oftentimes you'll see something that makes sense afterwards, but you didn't necessarily think about at the beginning as being a potential factor. And here that was the fact that we observed even more inorganic aerosols than organics when we sampled ambient air through the OFR. And that was because of the high NOx and the ammonia that were specific to the tunnel here. And then a conceptually similar study was done more recently by Liao et al. In Beijing, where they installed their PAM OFR on the mobile laboratory. And this is a research group at Peking University. And they had on this mobile lab a suite of real-time instrumentation, including their TOF ACSM, and they had a PTRMS, which a VOCs would serve a similar but better purpose, to be honest. But that was what they had to gain insight into the specific VOCs that are responsible for observed SOA formation. And so they drove around on the 4th Ring Road in Beijing, measured significant organic aerosol formation through the OFR, ranging from tens of microgram per cubic meter to over 100 microgram per cubic meter during a haze event. And with their PTRMS, they measured specific classes of VOCs, and from application of laboratory SOA yields for those specific precursors, attempted to explain as much of the observed OA formation that they could. And you can see that for the most part, the largest fraction that they can explain is from single ring aromatics like toluene or xylenes, which you would expect to be present in relatively high concentrations when they're on the road. But still, that never explains more than a really small fraction of the observed OA that they saw when sampling through the OFR. And so the interpretation that they posed was that the remaining SOA that was formed was from unmeasured lower volatility precursors to SOA, like intermediate volatility compounds and semi-volatile organic compounds that are harder to measure, but who have very efficient, very high SOA yields that are emitted from the mixed fleet of vehicles that are on the road in this study. And that was likely also the case for this study by Tachik et al. That IVOCs and SVOCs are the main contributors to SOA formation here. And you wouldn't necessarily know this until you made the measurement in situ, and that's where OFRs can provide significant value compared to chambers, which you can't take into the field to measure in the same way. And so here again is another study using an OFR coupled to this time Aerodyne's AMS at the CalNext during the CalNext campaign that took place at Pasadena in 2010. And so this is a receptor site that's several hours downwind of the Los Angeles metropolitan area in California in the U.S. And the same general trend is observed. You see a maximum aerosol enhancement formed after a few equivalent days of OH exposure before it then decreases due to continued fragmentation. But just here noting that when you're not, I just wanted to make the comment that when you're not as close to sources, the absolute enhancements while there and while real are significantly less because concentrations of precursors in the air are much less. During the daytime, when VOCs, IVOCs, and SVOCs have already been processed in transit from Los Angeles to Pasadena, there's less remaining at the site for continued oxidation, and that's why concentrations are relatively low here. But then at night, when there's less atmospheric aging, and when the mixing layer is also lower in the atmosphere, there's on average higher concentrations of VOCs at the site, and so there's higher SOA formation potential from OH oxidation of those same precursors when measured at the night time instead. And so this is one of many examples now where OFRs have been used at different receptor sites around the world to gain insight into the precursors to SOA formation and the SOA formation potential at given measurement locations. So now to switch gears and talk about some other slightly different applications and answer the question, what can be learned about SOA properties using OFRs? Here, I'm going to show some example applications using the OFR in an analogous manner to an environmental chamber, just as a source of different types of SOA, where measurements were made to learn more about their yields and their composition over multiple generations of aging. But then other logical questions to ask from these types of applications are what precursors are necessary to explain ambient SOA formation? So, for example, if a group has made ambient measurements with an OFR in situ and seen some sort of chemical fingerprint in the SOA or some estimated yield, they will often then take the OFR back into the lab and look at the oxidation of precursors that they think may be needed to explain that SOA formation. So in this sense, the OFR serves as a bridge from the field to the lab. But then in other cases, it may be of interest, as I said, just to use it in a similar way as a smog chamber, to look at the properties of SOA, such as their water uptake or their light absorption efficiency, and how they change with aging, and are they correlated in any way that can be parameterized in models. First, this figure is a result from a study by Karjalainen et al., where they looked at particle emission factors from a diesel engine, and they were specifically interested in looking at different engine aftertreatments on that diesel engine and how that influenced both the primary and the secondary organic aerosol emission factors. And so you can see where this might have implications for policy and regulations in this type of study, that if the primary component is what's regulated, but the gaseous emissions are what govern most of the aerosol that's formed in the atmosphere, this is where an OFR can be useful as a screening tool to gain insight into those questions. And Karjalainen et al. Saw that when they didn't apply any engine aftertreatment, they saw PM primary emission factors of about 5 milligrams per kilowatt hour of vehicle operation, but then a 5-fold increase in secondary aerosol emission factors relative to primary that would otherwise not have been known. They saw a similar picture with renewable fuel instead of fossil fuel, and then applying different oxidation catalysts and other techniques to remove primary aerosol. They had different levels of effect on the secondary emissions as well. So going from very high emissions to very low emissions, both primary and secondary, using specific combinations of engine after treatments and for different fuels. And there have been other studies in the literature that have also looked at these types of questions, but for different engines and also for other combustion sources, such as wood fires and even single vehicles on dynamometer studies. So this is a very common application of OFRs. They've been, especially now, OFRs are continuously being used more and more to look at the aging of biomass burning aerosols. And this is an example of using the OFR to age tar balls that are emitted from a combustion source in Dr. Chakrabarty's group at WashU St. Louis. This was published in EST Letters a few years ago. And what they saw was that when they generate combustion aerosols containing tar balls that was absorbing already, this brown carbon, as they age it further, both the imaginary component of the refractive index, which is proportional to its light absorption efficiency, decreases at the wavelengths that were measured with their optical technique, and then the single scattering albedo increased, as you would expect when the absorption decreased. So the aerosol, the brown carbon aerosol in this case, is being bleached by hydroxyl radical as it breaks up the aromaticity and the other chromophoric functional groups that are present in the primary brown carbon. And there have been a lot of studies that have accomplished similar objectives using OFRs in this framework. And now that we are now developing techniques to generate nitrate radicals, similar studies are being done to look at the effect of nitrite time aging on tar balls, which, as it turns out, has the different effect. That adds nitrogen-containing chromophores through the nitrate radical oxidation that tends to increase the absorption of the aerosol. A lot of groups have done studies to measure the yields of SOA from different precursors of interest, either motivated by field measurements or just motivated by the current state of the science and open research questions. Here is an example using an OFR to oxidize decamethylpentylsiloxane, or D5, which is a volatile chemical product that's used in personal care products and other anthropogenic sources. And you can see that as a function of oxidant exposure and precursor concentration, you can approach relatively high mass yields with this precursor. And many other similar studies have been, conceptually similar studies have been done with OFRs. And then here is an example of using an OFR to generate SOA with a range of composition to look at the hygroscopic properties. This study by Paganojo et al. Generated biogenic SOA from OH oxidation of isoprene, alpha-pinene, and longifolene, which have a range of different molecular weights and oxygen to carbon ratios, and saw that in general, when the more oxidized, lower molecular weight SOA had the highest hygroscopic growth factors, approaching 1.4 at the highest humidity that were studied. And then when you calculate the kappa values from these different SOA types, the kappa values of isoprene SOA measured in the subsaturated regime approach what was made with a CCN instrument at supersaturated regime, but that for other amorphous semisolid high molecular weight SOA materials like longifolene in particular, which is a sesquiterpene, there's a disconnect between the kappa value that was calculated from subsaturated conditions to what was measured in supersaturated conditions. So again, many groups have used OFRs in this sort of application. And then at the time that I originally made this slide a couple of years ago, this study by Chowdhury et al. Was one of the only studies that looked at the toxicity of SOA, but there have since been a few more. And this just shows that SOA with different compositions in terms of the amount of aging, whether it's relatively less oxidation or more, can change significantly the toxicity of the SOA as measured by, in this study, the cell viability. So the less viable the cells are, the more following exposure, particularly at these higher sample masses of SOA, the less viable the cells are, the more toxic the SOA is. And that was observed for both biogenic SOA and also anthropogenic SOA. So to summarize the main points from this talk, OFRs are being used routinely in the community now to look at and gain better understanding into OVOC and SOA formation and aging, both in the lab and in the field. It seems to be the case that perturbations of ambient air in situ with OFRs can, in some cases, aid significantly to the interpretation of precursors to OVOCs and SOA in the air that can then be followed up with targeted lab studies, as well as to aid in the interpretation of factor analysis of those ambient source factors using PMF and other types of principal component analyses. And I would make the argument that there have been enough applications and enough demonstrations of OFRs to this point that it seems clear to me that they can complement and extend what can be done with traditional conventional environmental chambers, but usually at much lower cost. For a while, there was some contention in the community as to whether OFRs are better or worse than chambers, and I've joined different sides of that debate. But at this point, I think it's a fair statement to say that rather than necessarily competing with them, they can extend what they do and they can complement what they do, and especially in cases where chambers are just not a viable option to deploy, such as in the field or in lab studies with limited space or limited personnel or budget. So I just want to close the presentation by just highlighting a few resources online. On a wiki that I maintain, we have an active list of publications for groups using OFRs. And all of the studies that I cited over the course of this presentation are tabulated in the wiki. We have an electronic manual that has some of the more detailed information about the PAM OFR itself. We have a users list. And I just did want to briefly mention test scoring here. So I've worked with a few distributors over the years to deliver OFRs to user groups. And for the most part, those groups, because the PAM is still a relatively new instrument and those distributors have not had formal training on it, mostly what they will do is they'll deliver it to lab, they'll open the box, they'll plug in the cables, and then just demonstrate it that it basically turns on, and then leave. I was really impressed when we delivered a PAM to IIT Delhi that test scoring went the extra step to learn how to use the instrument and to work with the user to do an OH exposure calibration before they considered their job done. So I think that if you decide that OFRs are right for your group, I think you'll be in good hands between support from myself and also from on the ground and from test scoring. So finally, thank you all for joining me again. It's been my pleasure to talk to you about our work, and I'd be happy to take questions.
Thank you, Dr. Andrew. It was a nice presentation with, you have covered a lot of case studies. We have now a couple of questions. I'll just read out one by one. So the first one is, what are the effect of humidity and temperature on formation of SOA?
It's a good question. The effect of humidity it's the first thing to realize is that with an OFR, when you change the humidity, you also change significantly the OH concentration as well. So in order to target the effect of humidity specifically on SOA formation, you have to be able to use the estimation equation that I developed or the model to decouple the effects of humidity on OH exposure from humidity. But that being said, heterogeneous processes that are humidity dependent may in some cases be residence time limited and are harder to study directly in OFRs. But otherwise, I think in most cases, humidity seems to, by making the aerosol less glassy, can change the rate at which materials diffuse through the bulk, and in some cases may lead to enhanced SOA formation, and in others, I guess could if it suppresses a ligament formation, might decrease the amount of SOA that's formed. Temperature, in most cases, I think will decrease the SOA yield just because of the volatility, and so if one wants to systematically look at the effect of temperature, it is more challenging to do that in OFRs because we don't have active temperature control. It's just whatever the ambient temperature is, and the lamps will increase the temperature by a couple of degrees centigrade just from their normal operation.
Mhm. So, like, what happens in dust-dominated area? Like, will the concentration of SO be high or low?
Was the question in a dust-dominated area, will SOA concentrations be higher or lower? Was that the question?
Yeah.
That's a really good question. I know that um, that in the earlier days of OFRs, when most of our users were based in the U.S. and in Europe, dust events were not really on our minds, and that was what led to one of the most prominent OFR users in the field being Professor Jose Jimenez at CU Boulder, even recommending that groups take off the front plate of OFRs when they can, for various technical reasons that I won't get into here. But they argued that it was advantageous to take the front plate off and just sample ambient air directly in without the front plate. That isn't necessarily practical in other parts of the world where dust events are a major factor. And I know that groups in China have struggled with this question, and I haven't heard anything specific yet in terms of what happens to the SOA formation potential of ambient air when there's a lot of dust there also. That's a really good question, and I'm sorry I don't know how to answer it just yet. But I hope that with continued growth and use of OFRs in parts of Asia, especially where dust events are just a part of life, that we can gain new fundamental insight into that question.
Mhm. Okay, I think the next question is also again on the humidity. So, what is the minimum humidity required to generate OH radicals inside the PAM chamber? Is it necessary to add extra water molecules if we are using PAM for ambient aerosol oxidation?
That's a really good question. Unless you're sampling in the R, usually not necessary to add extra humidity for ambient OFR measurements, because usually there's plenty of humidity that's already there to generate OH. So at a typical ambient relative humidity of 40% or even 30%, or up to 50, 60, 70, 80% RH, or even higher, plenty of plenty of water vapor already to generate OH, and you don't need to add more. You can generate OH at 1% relative humidity. It's just not very much. And there, the bigger risk is that the rate of photolysis at 254 nanometers can start to compete with the OH. But you can always generate OH if you have any humidity. It's just a question of whether it's enough to achieve as much aging as you want. But generally, 20, 30% RH on the low end is still plenty. And because in most environments there's much more humidity than that, there's no need to add more humidity. I guess the only other case where it may be necessary to add humidity is if you're significantly diluting the sample. And so that can sometimes be an issue when you're sampling directly the output from combustion sources like diesel engines or flames from a controlled burn. There, it can sometimes be useful to dilute what you're sampling so you don't overwhelm not only the OFR but the instruments with a significant amount of secondary aerosols that you're generating. And so most dilution air is not humidified as it comes out of the gas bottle. And so that's a case where if you're diluting by 5-to-1 or 10-to-1 the sample flow, that's the case where you would want to humidify the dilution flow. But for normal ambient measurements, I don't think it's necessary.
Mhm. Okay, another question is on the uncertainties, like any wall corrections are required, or how to quantify the associated uncertainties, and what would be the uncertainty levels in the instrument?
So I think the question might be I think the question is what are the particle wall losses in
Yeah.
OFRs? If that's not the case, stop me and address it differently. There have been a couple of studies that have explicitly characterized size-dependent wall losses of, say, ammonium sulfate aerosols or black carbon particles through OFRs by introducing monodisperse aerosols at the inlet of the OFR, and then using a CPC to measure a particle counter to measure upstream and downstream concentrations, and from there inferring the particle wall loss as a function of size. Every experiment is different and every particle type is different, but in general, I think it is a true statement that above 100 nanometers or so, wall losses are typically 10% or less through OFRs. Smaller particles tend to be higher losses because they're more diffuse, and so they through convection and recirculation in the OFRs that sometimes that does happen just as a matter of fact when the lights are turned on and temperature gradients develop. The losses of particles that are, say, 50 nanometers or so can be more on the order of 50%. But that is how groups typically will explicitly characterize it, as putting in a monodispersed distribution of aerosols and then systematically varying the size over the range of interest and then measuring the concentrations upstream and downstream. And to whoever asked that question, if you want specific examples of that in the literature, if you email me afterwards, I'll point you to some references that might give you a better example of what the quantitative magnitude of those wall losses are.
Mm-hmm. So what is the operational range for PAM in terms of humidity and temperature? And how easy to control these parameters?
I guess for field measurements, typically if you start with the situation where there's enough humidity already, you mostly would work with the humidity that's present in ambient air and not try to control it further. But if we were talking about a lab study where you are actively controlling the humidity, the system comes with a Nafion humidifier that when it's just used, when it's just fed room temperature water and dry air is flowing through it, a typical humidity could be, depending on the flow rate through it and any mixing or dilution with dry carrier gas, is typically about 50 to 60% relative humidity without doing anything. If you wanted to get it lower, typically users will add a second dry dilution gas to mix with it and then reduce it. So getting it lower than that is pretty easy. Getting it higher than that is not that much more involved, but it just requires some extra hardware that we don't normally deliver, because normally the 50 to 60% humidity generates a lot of OH. But if the humidity is a parameter that's of interest for other reasons, you can add more humidity by putting in probably the most effective way to do this, because I've done this a few times where I've needed, say, 90% relative humidity, is to install a heated recirculating water bath that recirculates heated water through the Nafion membranes. That increases the diffusion of water vapor into the sample stream significantly. And so, just to give you some approximate numbers, if room temperature is maybe 22 or 25 C, if water that's heated to maybe 30, 32 C is recirculated through that Nafion humidifier, can easily get 90% relative humidity. And I've done that a few times.
Okay.
I think the other part of that question was about temperature, I think. That is a little bit harder to manipulate directly, for the reason I mentioned earlier, that the lamps will tend to increase the temperature by a few degrees anyways. I don't think there would be anything stopping you from wrapping the OFR in heat tape and heating it to 40 or 50 C if you really wanted to do that. But that's not something that we equip with it to do on its own. But because every experiment is different, and the OFR is modular enough and small enough that can be done on a practical scale, that could be done if you wanted to go higher than, say, 30 C or 35 C to look at specific SOA composition or yield at certain conditions.
Mm-hmm. So the next question is, sulfuric acid was considered a major precursor in new particle formation. Does it also affect SOA formation?
It does. There have been a couple of studies that have looked at the influence of having sulfate seeds on SOA yields. And there are some cases where it can have, so this is, the answer that I'm about to give is maybe less focused on specific nucleation at very low concentrations, but at under conditions where there are high concentrations of particles and you get condensation and growth of semi-volatiles on top of that. So I can't, from my own experience, I can't speak directly to how sulfuric acid influences cluster formation at relatively low particle concentrations, but I can say that when you have sulfuric acid seeds in the OFRs, which by the way are very easy to generate by just adding SO2, there are cases where that can enhance the yield significantly relative to cases where there's neutral seed or where there's no seed. And the most well-known system for that I'm aware of is isoprene SOA, which forms species that are taken up into the aerosol from reactive uptake and that are whose uptake is enhanced by acidic conditions like sulfuric acid. But there are likely other systems out there that I'm just not aware of where sulfuric acid can play a role.
Okay. Yeah, one last question. Is it possible to perform aqueous phase reactions like sending atomized droplets? And is it possible to collect the droplets, condensed liquids from the PAM reactor for further analysis?
That's a topical question to ask because I had a conversation with a colleague on Friday about whether aqueous phase chemistry can be done by sending in droplets at high humidity. And I think my answer to that question is I don't see why it couldn't be done. This user was asking specifically about sustaining humidity at 95% relative humidity or something like that, I think. And I don't think there's any reason why it couldn't be done, but it certainly has not been a focus of other research groups to this point that I know of. And so I just want to give the kind of caveat that I gave to the other user in this case, that it probably could be done, but it hasn't been done. And so that represents potential area where there are major contributions that could be made because it hasn't been studied, but I just don't have a lot to go on from direct experience yet. But no reason why I think it couldn't be done. It just may require some learning and optimization in order to figure out how to do it optimally.
Okay. Okay. So that will bring us to the end of the session. Thank you, Dr. Andrew, for your very detailed presentation. And I thank all the participants on behalf of Tescon Aerofluid Incorporated. So see you next time in the next webinar. Thank you. Bye-bye.
Thank you, everyone. Bye.